that we need to partition the set of users into disjoint sets. Each set must have at least k users. And also we have an optimization goal of minimizing the sum of ASR areas, right? Why? Intuitively, the cost of the query processing is proportional to the area. So the solution proposed was an heuristic. This problem is NP hard, even in 2 dimensions, right? Finding an optimal solution. So the heuristic proposed was based on fractals, dimensionality mapping. Are you familiar with the Hilbert fractal? So just a few words. This is not the main topic of this talk. So we have a 2-dimensional space. We split this space according to a regular grid. And then there is this curve, which is defined recursively. We can have various levels of granularity. The idea is that this curve traverses each cell of the space exactly once. And the order of the traversal gives an integer, a number for each cell. When a location falls within a particular cell, it has that associated number. For instance, this cell would be number 8, right? To have another example, a sample distribution of users will be mapped probably to something like this. And then within the sequence, we can simply split the 1D sequence into blocks of users of at least k. And this will determine the generated cloaking regions. This method works well if users are stationary. But that's not the case to happen in practice. Most of the time, users will move. And if the users will move, the sequence will change. If a user issues a continuous query, which means that the same query is generated at multiple timestamps from different locations. For instance, if I travel in my car and I want to have a constantly updated list of what is the nearest restaurant to my location, right? Let's say that I will post such a query, and then the server will send me back every minute the new set of results, which will change. Because I will change my location and I will appear in each ASR, it will be very easy for an attacker to do a simple intersection and see I must be the query source. So this method does not work for continuous queries. There was another method, and this is the last related work method that I will present. This was an SSTD 207 paper, which proposed the following simple fix. We can take the first snapshot of the continuous query and apply any reciprocal method on top of that, for instance, Hilbert Cloak. Then we freeze this set of users, and at the next timestamp, when the users will move, we will get a new ASR, which is their bounding rectangle. Obviously, there are 2 problems here. The first problem is that this rectangle will grow very large if the users will move in different directions. So maybe this would end up to be the entire data space. This is not practical. And the other problem is that if at least one user in the initial set will drop or disconnect, then the privacy of all other users is compromised, right? So with all these things discussed, can anybody help me summarize what are the motivations behind our work? Why do we want to have a new method? So what are the problems that we have seen? No? Yeah.
Retaining anonymity while in the move.
Okay, so handling continuous queries, right? Privacy for continuous queries. This would be one factor, right? So existing methods cannot achieve privacy. Something else?
Reducing cost of queries.
I'm sorry?
Reducing the cost of the queries.
Okay, so that would be minimizing the regions, right? Okay, very good point.
If there are few users or one user, how to protect a single user in such case?
Well, yes, there's a very good point. So we assume that the query is not issued if there are not enough users. We can protect against that. But you made a very good point, because there is a business model here that must be, in the end, sustained. And I will formulate it as considerable overhead for sporadic benefits. If I ask a query once a week, but I have to report my location every minute, such that other people can ask queries, would I really want to do that? Right? So this is one problem. The other problem is that in order to have these ASRs at a decent level of extent, we're going to need a lot of users. So we're going to need a lot of a high user density, right? And where are we going to get all these users from? Can we pool as a service provider? Can an anonymizer subscribe so many users so this method gets to be usable? Another problem, very important. There are a lot of assumptions on trusted entities. We assume that the anonymizer is trusted. That's fine, but what if it gets broken into? Furthermore, it is a bottleneck of performance, right? Then we assume that we have non-colluding users. But what if some attacker will subscribe with 1,000 users, fake users, decoys, and will upload some bogus locations distributed all over the data space? Whenever the attacker will intercept an ASR, he can filter out those users, and then he exposes the actual query source, right? So this is a fundamental problem regardless of the geometrical transformation that we use. So the questions that we want to ask is, can we have privacy, provable privacy for continuous queries? And if we do this, can we do it in such a way that we do not need to rely on other users? And if we can do that, can we do it in such a way that we don't need a centralized component? And there is another point here, and a very delicate point. Anybody want to make a guess? We discussed about this K anonymity. What about K? Do you think that this is convincing enough? What should we set K to? Is it 10? Is it 100? What is enough privacy? How can we define enough privacy? And then there is the trade-off. The larger the K, the larger the size of the SR, the more overhead. So can we achieve all these tasks and at the same time have some privacy, let's say, measurement which does not depend on any parameter? And instead we could have something as follows. All the attacker must find out is that I must have a mobile phone with a GPS device. This is definitely a stronger privacy guarantee, right? So can we do this? And we believe we can. And I will move on to discuss our technique. But before that, if there are any questions so far. Okay, I guess we can carry on. So as I mentioned earlier, we do not use spatial cloaking. We use cryptography. In particular, we use Private Information Retrieval, or PIR. So let's see how PIR works in a nutshell. We have on the right-hand side the server, a generic server. In our cases, there'll be a server. But for this particular case, we assume some very simple data format, a binary string, x, with elements x1 to xn. On the left-hand side, we have a client. This is a two-tier architecture. There is no intermediate anonymizer. So what Bob wants, the client, he wants to retrieve the item xi. Okay, so the search is based on index. However, he does not want the server to find out the value of I. So what is he going to do? He's going to encrypt this value of I, and I'm going to use the term encryption, although strictly speaking it's not encryption because there is no associated decryption, but I'm just going to use the term encryption. We can assume here that we say hidden. So it encrypts this I index into a query key of I. And this query is sent to the server. It is computationally hard for the server to determine the value of I based on Q of I, right? What the server will do will process the query and will return a function which is the result R, a function of the entire dataset X and Q of I. And based on this result, Bob can easily find Xi, the value of Xi, and this is done using a trapdoor function. I will show shortly how. A few mathematical properties. I will just skip very briefly over these. So the PIR protocol that we are using relies on the assumption that it's difficult to find out whether certain large numbers have a certain property. And the setting is the following. We have two large primes. This is similar to if you want the RSA setting, right? Standard encryption. We have their product n. And then we have the set QR. QR is the set of quadratic residues. And it consists of those numbers which are prime to n, and also have the property that there exists another x, so the numbers y in which are prime to n, and for which there exists x, such that y equals x squared in modular arithmetic. And based on this definition, we can define the